Hello, my name is Elise Van. I'm an education researcher at TERC, and today we're going to be presenting a paper for the END conference, Spatial Reasoning with a Human Scale Geometric Puzzle. I'm joined today by my colleagues.
Ken Raffanan.
And Teresa Lara Malloy, and also Jennifer Knudsen.
And we're representing the work of a larger team that also includes colleagues at Family Connection Center. This project is a co-design project that adapted an existing set of in-school curricular materials that were focused on math, spatial reasoning, and making to be used in an after-school program, Family Connection Center, which is a community-based organization in California in the United States. We also did an additional pilot at a second site that we'll speak a little bit more about later. The three of us supported facilitators through hands-on professional development sessions, which you can see pictured here. We worked through the same projects that the facilitators would be doing with the youth so that they would have the experience as the learner going through the projects. As I mentioned, we were at two sites for this program. At site one, we were at an after-school program working with youth through three larger units that focused on math, making, and 3D printing. The second unit is the one that we'll be really focusing on today, which focused on a Soma cube puzzle. And they were engaging these units over a period of 5 months, sometimes once a week, sometimes less frequently, but we were going in and supporting implementation over a longer period. At Site 2, we were working with youth just over a period of 2 days during a spring break camp, and we just focused on the first two units. And again, we'll be focusing on that second unit, the Soma cube puzzle today.
So the Soma cube puzzle was developed in the early 1900s by mathematician Piet Hein. It's often found as a wooden puzzle. Next. Okay. The way that we progressed the activity is that the youth were first challenged to make the 7 pieces of the Soma cube puzzle using small linking cubes, like you can see there on the left. They then put together those pieces into a 3 by 3 by 3 cube. And then in pairs, the youth made human scale puzzle pieces with 1 foot by 1 foot by 1 foot cardboard boxes. You can kind of see that there in the middle picture. And then in teams, they put together this human-sized Soma cube puzzle into a 3 foot by 3 foot by 3 foot cube, as you can see there on the right. So to assemble the linking cubes, the youth had to use all 3 types of spatial reasoning skills: the spatial perception, mental rotation, and spatial visualization. The youth embodied the spatial concepts of 3D rigid transformations, rotation, and translation. And in the large Soma cube, the youth stepped in and out of 2 different perspectives: an embodied perspective as they moved the puzzle pieces, and then an observer stance when they moved back to observe someone else putting in a puzzle piece, kind of offering a bird's eye view.
At Site 1, when the youth were working with the linking cubes, the smaller pieces, each youth was able to successfully create the set of 7 puzzle pieces, sometimes with hints from the facilitator or by seeing what their peers had created before them. Most went out to find and assemble at least one full Soma cube solution, but there were quite a few kids who lost interest as they struggled in creating that first Soma cube. When it came to working with the human scale cubes, some of those previously disengaged youth were very active participants with their peers. The fact that the cardboard pieces were so large, it really demanded their collaboration. All 18 youth initially worked together to assemble the cardboard Soma cube, and then they were mostly following the lead of one of the youth who had completed a smaller version successfully. And then the facilitator divided the class into smaller groups of 5 to 6 youth so that they had a lot more time to interact with the cube while they were working. At Site 2, some kids really found the 7 Soma cube puzzle pieces very fast, but others struggled a lot. They just gave up really easily, and they required a lot more hints from the facilitator. Some of the youth also were able to assemble their cube after multiple attempts. and they did show a lot of persistence. However, there were a few others that just gave up after their first failed attempt. But with the human scale cubes, there were pairs of trios who collaborated on building the Soma Cube puzzle pieces. There was a lot of joy and make-believe interactions. The kids on the right are showing us when they were working, they put two pieces together to make a lemonade stand. And as a group, they spent like 30 minutes trying to build a Soma Cube. And although there were a lot of youth who persisted, there were some kids who moved on to other activities. And then finally, there was a group of 2 youth who chose to solve the cube with a smaller 3D printed version, and then they used that to replicate with a solution with a larger group.
What we really found was that this human scaled puzzle, the large version of the puzzle, really had increased engagement among the youth, very active participation, and more successful solutions as students persisted in trying different ways to solve the puzzle. And this case really shows the promise of using large-scale objects for supporting the development of spatial reasoning skills in ways that engage youth. Because spatial thinking is associated with success in STEM disciplines, including mathematics, these activities are particularly important for students who are historically marginalized. Some other takeaways are that the scale encouraged collaboration among the youth. The size might also encourage users or learners to need to mentally rotate the object since it's difficult to actually physically rotate it. And the pieces being large might also necessitate that youth engage different muscle groups and movements to do rigid transformations. And communicating ideas about rotations was challenging for youth, so they had to really lean into learning to using some vocabulary around spatial rotation. We'd like to thank the facilitators, staff, and youth at Family Connection Center and at our second site. We also thank the Mathematics, Spatial Reasoning, and Computational Thinking through 3D Making Impact Research Project for the materials, and TERC for the internal research grant that supports this work. The work presented here was also in part inspired by the Making Math Visible project from George Hart and Elizabeth Heathfield. If you have any questions, please feel free to reach out to anyone on the team. We would love to hear from you. Our emails are here. And thank you so much for watching.